Hello, we are ME Team 50, and this is Bearing Load Measurement, presented by Andrew Bauer, Sean Young, and myself, Michael Hill. Our faculty advisor is Vito Marino, our sponsor is RBC Bearings, and our industry advisors are Phil Smith and John Cowles. In working with RBC Bearings for this project, we hope to research, design, and fabricate a cam and cam follower rig capable of safely generating an industry standard bearing load on a cam follower and accurately measuring this load using strain gauge instrumentation. This project hoped to measure load on a cam follower through only the use of a strain gauge. This gives RBC Bearings customers an accurate load estimation in industry without needing to modify their operations to incorporate a load cell. As part of this project, some goals and deliverables were to conduct analytical simulations to understand distribution of strain on cam follower bearings, including ideal strain gauge placement, determine a necessary load cell and compression spring rate for sufficient load and strain, develop a relationship in the form of an equation relating load and strain distribution on a cam follower, and then ultimately assemble the rig and conduct testing to validate the previous load and strain relationship.
Here is the rig that produces the force on the bearing of the cam follower. The cam spins, driven by the motor on a 40-to-1 reduction chain drive. From the rotational motion of the cam, it translates to linear motion of the midsection of the rig. This displacement caused by the cam compresses the resistance spring and produces a force of about 1,000 pounds. This force acts upon the bearing of the cam follower, as seen in the top right image. In the bottom right image, we can see a cross-section of the SolidWorks model where there are flats on the cam follower. In these flats, there are two strain gauges that measure the strain that results from the load on the bearing. Here is a physical model of where the strain gauge is actually placed. Here is the rig in motion. We can see that the rotational motion from the cam translates to linear vertical motion of the cam follower and cam follower housing, in which the springs are displaced, providing the force for the cam follower.
One of the most important parts of our rig design was the creation of a cam follower housing which could be used to support loads over 1,000 pounds applied to our roller bearing. On the left here is our first iteration, which had a high load which resulted in a lot of bending. From here we switched to our second iteration, which was a rib design to help prevent bending, and also came in separate pieces to allow for easily acquired stock sizes. From here we created our 3D printed mock-up, which allowed for confirming accurate hole locations among other things, and we eventually landed on our machined final design, which was hardened and reamed to accurate dimensions, which fit well into our rig.
With the cam follower rig able to safely generate an industry standard bearing load, our attention shifts to developing an analytical relationship between radial bearing load and strain distribution on the cam follower in ANSYS static structural analysis. Both normal elastic and shear elastic strain distributions in all directionalities are looked at in choosing the strain to be utilized in the strain load relationship. The consistently highest amplitude strain measured across the cam follower is normal elastic strain in the Z or axial direction. Thus, linear strain gauges are used in our study. In deciding the placement of the strain gauge, three requirements are considered: proximity to the roller bearing, consistency in strain readings, and protection of the strain gauge from damage. The midsection of the cam follower stud fulfills all three requirements and is therefore the optimal area to place the linear strain gauges. As seen in the previous slide, two single grid linear strain gauges separated by 180 degrees are to be placed on the cam follower stud. By having one strain gauge placed at the top of the stud and another at the bottom of the stud, the difference in strain can be determined. If the strain differential is constant across different axial preload values, our model is preload independent and thus only radial load will impact the value of the normal elastic strain differential. Preload independence is achieved in the region specified in the graph. More importantly, the difference in strain is utilized as a strain value in our load-strain relationship. The analytical load-strain relationship for a specified preload is displayed in the bottom left graph.
Here is our LabVIEW data acquisition dashboard, where we see real-time strain data on the left graph, strain data over time on the upper right-hand graph, and our load data over time on the bottom right-hand graph. We use the difference in the two strain gauge readings in combination with the equation from the simulated ANSYS model to predict the load on the cam follower. In yellow is the predicted load from the cam follower based on the strain gauge readings, and in orange is the load from the actual load cell. In yellow, the strain gauge reads 0 on the base circle of the cam. This is why the lower value is at 0. However, the max load generated is still the same as the predicted load.
Therefore, we accomplished our objective in determining that an accurate load estimation can be found using only a strain gauge on the body of the cam follower. As recommendations for continuation, we would like to see wireless technology implemented for capturing strain voltage readings of the rig remotely, as well as making bearing load measurement systems more easily adaptable to different cam and cam follower configurations.
We are Group ME50, and thank you to all of our sponsors and advisors who have helped us.